Hi. So it's me again. So yesterday I talked about just going from infinitely repeated games, from having one state, a static environment, to just having two states. So the simplest dynamic game I could really take. Today I'm going to talk about richer state spaces. So more states, more places I can go to try and see what happens in these different games. Okay, so previously we looked at Infinite Horizon games with one state with Guillaume, who looked at the PD games in more depth with different kinds of monitoring structures. Yesterday I looked at two states, variations on a dynamic prisoner's dilemma, where our decisions to cooperate change the incentives by increasing the stakes tomorrow. They also increase the temptations to defect. Additionally, we looked at a two-state game with an active and an inactive state. So we could choose to move to the inactive state at any point. We found outcomes consistent in both of the games with two states with history-dependent play. So when efficient SPE are easy to coordinate on, they're fairly simple. In particular, Grims and Tit for Tats are SPE. When there are clear gains to playing history-dependent strategy play, and in particular, when the basin of attraction for the MPE, which would be in an Infinite Horizon PD game, always defect, and in my games, playing different actions in different states, the basin of attraction on MPE, when it's small, we're more likely to get history-dependent play. Okay. So, a natural question for one of the motivations for Markov is that in a complex world, maybe we move towards simpler strategies. And Markov strategies are going to be the simplest ones we can pick that are going to be consistent with rationality. So, does selection of Markov perfect equilibria occur more frequently in richer dynamic environments? So that's what I'm going to try and look at today. I'm going to survey what literature there is on this. Maybe I might end 10 minutes early because there's not so much literature, but you probably won't be that disappointed. Okay, so I'm going to think about richness and complexity in a quite restrictive way. I'm going to think about it just as the size of the state space. I'm going to try and break this richness up into a dichotomy. I'm going to think about richness that comes from just having non-persistent shocks to the payoffs, so payoff-relevant shocks, and having more states that we can endogenously reach along the path of play, and that we can visit from any point in the game. We can get to any particular state by playing particular actions. Okay, so I'm going to motivate that by first looking at two games which are going to move from the core dynamic PD game I showed you yesterday, the two-state high and low PD game. Okay, so first off, I'm going to look by adding payoff shocks. So I'm going to take a state space. I'm just going to take the endogenous states, and I'm going to take the product with a set of shocks. My transition rule, I'm just going to be acting on these endogenously determined states, and my shock is just going to be an independent shock drawn from some distribution. Because these shocks are payoff relevant, Markov strategies are now going to be functions from the endogenous states and the shocks into potentially mixed strategies over my actions. I think last time I defined the selection profiles. I'm still going to focus on pure strategies for the most part, and more narrowly at symmetric pure strategies. Okay, this was my original game. So I had a low state, a high state. The high state was unambiguously better than the low state because the worst that could happen here was I get 130. The best that could happen down here was I got 125. If we both cooperated in the low state, we managed to transit to the high state. Only if we both defected in the high state did we go back down to the low state. So this was my original game. We found that we got quite a lot of history-dependent play in this particular game. So what I'm going to do is I'm going to add shocks to these payoffs. I'm going to take a value x, which is uniformly distributed across -5, -4, up to 5. And I'm going to add, in the low state, the shock x to the cooperation payoff. And I'm going to subtract that shock from the defect payoff. So the difference between the two is going to be 2x. Up in the high state, if I play cooperation, I'm going to add 2x to that payoff. In the defect state, I'm going to subtract 2x. So the difference between the two is going to be 4 times x. So at most, 20. Okay, so that's my shift. So I've gone from having 2 states to having 22 states. So this is an order of magnitude increase in the state space. Before, we had 4 pure strategy, symmetric, Markov strategies. Now that I have this richer state space, there's 1.4, well, it's a little bit less than 1.4 million, but I have many, many possible Markov strategy profiles. This is just the symmetric ones. Looking at the asymmetric ones, there's a lot more, obviously. Okay. But by construction, by my choosing these shocks to make them fairly small, the unique pure strategy, symmetric, Markov perfect equilibria in this environment is to ignore the shock x. That when I'm in the low state, I should cooperate. When I'm in the high state, I should defect. There is no other symmetric MPE of this game. There are some more asymmetric ones, but they don't particularly alter the game if I start out in the low state. Okay. My interpretation of this is that I took a perturbation of the original game. I added fairly small shocks to the actions. It's not really changing the core strategic tensions in this game. The largest difference comes from going from low to high. I still have a large shift here between joint cooperation and the temptation to defect. Mostly, the game's tensions are the same. All I've changed is an order of, well, not all I've changed. Apart from the small shift in the shocks, I have an order of magnitude shift in the complexity if we think about the size of the state space as complexity. Okay, so I'm just going to go straight to results. I used these graphs last time. So this is the original game without shocks. This is the game with the shocks. There's 3 bars in each state. I'm just going to focus on the endogenously determined states. Supergames 1 to 5, Supergames 6 to 10, Supergames 11 to 15. The white dot is the initial play for the low state, the first period, because we start in the low state. In the high state, I can only possibly reach this in the second period. The white dots are the second period cooperation rate, which necessarily required joint cooperation. Black dots are the cooperation rates in all periods except for the first time I'm in that state. Okay, so the difference between the white and the black is maybe giving us an idea of the size of history dependence. But there are some changes to this game. In particular, in my original game, across the session, cooperation dropped off. So in the last block of 5 super games, my cooperation rate had gone down from about, 55, 60, about, let's say 70%. It had gone down to just over 50%. Here, in the game where we thought that we might select Markov more, we actually have the opposite outcome. Markov would suggest that we're going to get 0% cooperation here in the high state. Instead, we've seen an increase. It's also in the initial play. The initial play is larger in the high state as well. Okay, so it doesn't seem like just complexity on its own is going to drive the game to the Markov perfect equilibria here with shocks. If I look at the supergame histories, in these graphs I was taking each supergame and taking the pair, what's the cooperation rate in the low state, what's the cooperation rate in the high state, ignoring the shocks, and then graphing each pair with, if there's more mass at a particular point, I'm going to make a bigger bubble. This was the original game, so we had about 12% down here where the Markov perfect equilibria was, and we had about 17% up here in the top right corner, which was joint cooperation, or cooperation here. Sorry, this is individual level. Here is the Game+Shocks, so going between these two things. What we see is a shift towards the top right corner. We're in fact getting more cooperation. We're moving away from the Markov perfect equilibrium. Okay, I estimate the strategies using the strategy frequency estimation method. So I'm going to restrict attention to the original strategies that I was using in my two-state game. I should shift to using a larger class of strategies. In the paper we don't see too much action. So I should condition on X within the strategy too if I'm going to assess this. But as a quick pass, this is going to be okay, I think. I get quite a lot of the SCD strategy. This is cooperate. As soon as I observe a non-cooperation from non-joint cooperation, I switch to the Markov, cooperate in low, defect in high. MCD is the Markov strategy. Here I do see about 14% of this Markov strategy, but in the original game I saw about 20%. So this is almost halved. And then I additionally see the strategy MCC. So it looks like unconditional cooperation. If I throw a couple more strategies in here, you actually find out that this looks like a Markov strategy, which is cooperate for all shocks which aren't too large. So when the shocks are between -5 and -3 in the high state, they defect. So here I can just try and look at what's the cooperation rate. Oh, sorry. We did, Grim is in there. SDD, so reversion to joint defection forever, yes? SCD would be...
Well, that was the sophisticated one where you
yes.
cooperate, but then you switch to a Markov strategy.
So yes, but the Markov strategy I switched to is MCD, cooperate in low, defect in high.
Yeah,
Grim...
I'm asking simply about Grim. I mean, if the guy doesn't cooperate, you just go for defect always.
Yes.
Or keep for that.
So that would be what I would call the strategy SDD, a trigger which moves to defect in both states forever, yes?
Yeah.
I include that in the strategy. It does not get much action. Or in the estimation procedure, it does not get much action. It could be because a lot more of the time they stay in the high state and I don't get to see them come back down to the low state to see what they would do.
The game that you talked about yesterday, you found a considerable percentage of tit for tat, no?
I saw more tit for tat in the original game. I also saw these two, the three strategies were these two and tit for tat.
Yeah.
What I see is a substitution away from tit for tat towards a more cooperative strategy, which actually is just conditioning on the shocks. Yeah?
This is about almost 50% of the Markov strategy.
Yes. This, yeah.
More than what you observed in the other?
Yes. It depends on how we interpret MCC. It could be that this is a Markov strategy, or it could be that it's a more lenient strategy that I haven't included in the estimation procedure. I could include many more strategies. There's so many things I could be conditioning on in this game. We thought to just keep it simple and just use a very restricted set of strategies that for an as-it.
How many non-Markov strategies do you have?
We have, I think, in the estimation that this is from, we have both versions of the trigger with CD and DD. We have tit for tat, we have suspicious tit for tat, we have an asymmetric strategy which starts out by defecting in the high state to try and do efficient alternation between CD and DC with a reversion to MCD with reversion to MDD. So we have a couple.
Previous slides were saying it was less Markov, and now it was saying, oh, look, it's more. So there's some disconnect between the frequency estimation and your other
Yes.
other ways. And so it'd be interesting to hear what's going on with that.
I think this involves us playing with the strategies that we're putting into those games to try and see if there's other history-dependent strategies which would do better, which we haven't done. We've included many more Markov strategies, and what we do find is that, where am I? Okay. This goes down to about 20% if we include other Markov strategies which condition on the shock X. So it's just a substitution amongst Markov strategies. So we're finding actually something which, if I include more strategies, it is Markov, in fact. It's just not consistent with the Markov perfect equilibrium.
Okay. Yeah, that's very different.
Pardon?
That's very different. It's a different statement.
Yes.
Because when you say that increasing complexity doesn't sequence people towards Markov perfect, mean that Markov perfect equilibrium. Well, perfect.
Yeah.
But you're seeing a movement towards Markov strategy.
Yes, so this could be that the complexity is pushing them towards simpler strategies which aren't punishing in a way that would make it...
More complex environment, I think, equilibrium perfect. So, is there any, one of the things we didn't talk about was how close anything looks like equilibrium, what fraction of people were getting close to the payout they could be getting if your PDC estimates were right. Is it 3/4 of them, or it's almost none, or what?
Yes, so I don't have that yet, so I can't tell you. It's something we will do, though. Yeah. So yeah, no, there's a lot to do on this paper, actually. Okay, so I do want to motivate, though, that they are responding to the shocks. Even though, so it just seemed that there was more cooperation, what might they be using these shocks for? So here I'm showing you the first period cooperation rate. So they enter the beginning of the Supergame, they're in the low state, and here this is Supergames 1 to 5, 6 to 10, 11 to 15. So the black bar is shocks that were less than or equal to -3. The light blue is greater than or equal to 3, so on the upper end, and then the darker blue, or the middle blue, is those in the middle. So here on the initial period, there doesn't seem to be that much response to the shock. There is a positive response. The higher shocks are associated with more cooperation. As the session evolves, they do cooperate a little. This is significant. They do cooperate less when the shock is negative in the first round. If I look at the second period, conditional on getting up into the high state, I see a much larger response to the shock X. So here, the size of the shock is 2x on C minus 2x on the D action. And I see much less cooperation initially when I get up into high. When the shock is low, much more cooperation when it's high. This effect becomes smaller as the Supergame as the session proceeds. Okay.
So in fact, you end up with less dependence on the shock.
Yes, that it starts out
Than
much larger.
Than what initially was.
Yes. So they learn to use the shock less to condition their initial response in the high state. So the high state, when I was talking about the basin of attraction, the high state is where strategic uncertainty was being realized. If one player is playing MCD and the other player is playing SCD, well, this player is cooperating, this player is defecting. So here is where we realize that we're using different strategies. In the first period, we both cooperate under both strategies. So X2 is going to be an important payoff relevant variable for the strategic uncertainty. So if I include X2 in the basin of attraction, it would predict that I should get variation in the cooperation rate in this manner. So I'm going to say that the second period shock is helping to get rid of some of the strategic uncertainty. They're using the shocks to help them coordinate on cooperation. I'm not able to go more deeply into what's going on with the shocks. I can just tell you that there is a relationship in the second period. It's much stronger than in the first period. Okay, so the result in this is that despite an order of magnitude increase in complexity, subject's behavior, I'd say, is qualitatively similar to the core game with just two states. Small perturbations to the game structure yielded qualitatively similar behavior. So I'm going to think about this as being small causes, small effects, but not over the Markov selection, but over the equilibria selection. We also see a larger response to X2, which is predicted by the basin of attraction index I motivated at the end of the last lecture. Okay, so adding states through small shocks does not lead to a greater selection of Markov. The alternative option might be to add more states that can be endogenously reached along the path of play. So I'm going to do that now. It's going to be hard for me to add an additional 20 payoff tables to this game and make it something that subjects can understand. So I'm just going to add 2.
Didn't you say the opposite of the first one?
Adding states. I said I'm going to modify that to Markov perfect equilibrium strategies.
What?
I should modify this to adding states through small shocks does not lead to greater selection of MPE strategies.
Markov
Equilibrium strategies.
It does lead to a greater selection of Markov.
The behavior is consistent with a greater selection of Markov strategies. Because they're cooperative, it may be that they're cooperating at such high rates, they're not triggering the punishments, and I'm not able to detect those. Because they're in the direction of cooperation. But you're right, I do get more behavior that's consistent with Markov, so I need to pull this back to Markov perfect equilibria.
Try doing a cruder non-statistical count of frequency of Markov within subject.
With frequency of...
How many times you've been in this state? And if you're using a Markov strategy, you should always be doing the same thing in this state. Because if people are playing history, if yesterday's history or effectively, if history makes a difference, people aren't Markov. So it's
Yes.
to be able to classify individuals how Markov they are.
So I could use more of the power, use the individual level.
Yeah.
Yes, I looked at individual.
That is, this wouldn't be instead of the frequency, it would be a complement. It would be reassuring, it would be different ways of looking at things.
And you got similar answers.
You get very different answers.
No, that would be...
It's also nice because you don't need no apparatus and maximum likelihood.
So I looked at the individual level estimates myself. I have those like graphs with the colors, and it was just me looking for patterns. So I haven't done a formal statistical analysis. But that would be nice to back this up and say whether it might be Markov strategies or it's actually something which is more history dependent.
But this is going to work better, I don't know the data, if people are switching across strategies, if they're still...
Right, so I'm doing these little fall and left for Supergame, for example. This settled down a while, but that was hand strategy.
No, but they could, if they're switching strategy.
So
I don't know.
I know, but still, something to know. Yeah.
So this is, I have this figure. This is at the Supergame level. I have a version of this figure at the subject level. So I could begin to use these. I'll take the marginal of one of these distributions and then run a distributional test on it. That should also, I'd have to take out the shock as well. But I guess so long as they have enough values of the shock, that shouldn't make too much of a difference. But that's another way I could run a test. Now I'll do that. Okay. Okay, where was I? So I'm going to add 2 new states to the game. So I had my low state, I had my high state. I'm going to add a very low state at the bottom. I'm going to add a very high state at the top. So I'll go through what the payoffs are here. Just let me tell you, I've got to modify the transition. I need to find a way to get from high to very high, a way to get from low to very low. My transition rule is just going to be each time we see joint cooperation, we go up a state until we reach a ceiling in very high. Each time we play joint defection, we go down a state until we reach the floor of very low. That's my transition rule, just in words. I did it in colors too. I don't know if you can see the green. Is that hard to see? Okay. Okay, so this is going into this is the state that we thought was going to make a difference. This is the one we thought was going to drive the selection of Markov. We had priors every time we ran sessions, we thought this is definitely going to give us Markov. We were continuously wrong. Okay, I pretty much am telling this actually will go towards Markov, or a little bit. Okay, so in my high state, I have the original payoffs. The only thing I've changed is now if we play joint cooperation, we move up into the very high state. My very high state is a prisoner's dilemma again, but it's got the same payoff from joint cooperation, so if we manage to succeed at joint cooperation in all periods, I'm going to get exactly the same payoffs that I got in my original game. However, I've ramped up the temptation to defect from joint cooperation in this state. Instead of being an additional 80, it's additional $1.80 here. If we jointly defect here, we get a very low payoff of 85. So if we were to alternate between very high and high, this wouldn't give us a very good payoff. And the sucker's payoff up here is just 10. So it's pretty risky to try and coordinate on cooperation here. So this is why we put this game in. We wanted to maintain the same efficient frontier, so we make sure that 380 plus 10 divided by 2, that's less than 280 plus 130 divided by 2. So I have the same efficient frontier. I have the same payoffs if I sustain joint cooperation. We thought that by adding this state, they would go up into this state, they'd learn that they get the bad outcome up here. Maybe this would push the game towards Markov perfection. The low payoff, we set cooperation to be a dominant strategy in the stage game. So I'm going to get at least 40 if I play cooperate, at most 20 if I play defect. So we're expecting people, if they get down into the very low state, to cooperate. We set the payoff here, CC equal to 60. So individually rational punishments, well, if I wanted to sustain defect in my original game, I would force the payoff of 60. I'm going to continue to get that. It's just now alternate between very low and low. This is our motivation for why we chose these numbers. There's lots of other numbers we could probably have chosen. We're now a little bit committed to these numbers. Okay. Okay, there's a unique symmetric Markov perfect equilibria in this game. It's going to be the analog to the one we had in the original game. We cooperate in both the very low and low states. We defect in the high and very high states. I'm going to start the game in low. So under Markov in my original game and this game, we would have the same path of play, the same payoffs, the same temptations to defect from the agreement. Which would be less than we would make by following the agreement. Okay. The analogs to the asymmetric Markov in this game are the same. It's going to have the same asymmetric one. Basically, I've eliminated the low state with the dominance, and the very high, the temptation is just too much. Okay. So we're going to call this strategy M-C-C-D-D. We can also sustain still, for my value of delta equal to 3/4, joint cooperation. So we could think about the strategy S-C-C-D-D. That's cooperate until I observe someone defecting, and then I switch to this Markov strategy. Okay, results. So now I need to show you the cooperation rates in the very low state, the high, and the very high. And that's what I'm doing here. So this is my modified game. The label we can ignore. This is the one with the extended state space. This is my original game. So the first thing to notice is that the initial play in the game, so we start out in the low state. These white circles in the low state are telling me before I see anything which other people have done, I have to choose how much to cooperate. We get a decrease in cooperation to start the game of about 10%. We see a larger effect of history dependence in the low state. So when I come back to the low state, my cooperation rate here is much lower. Drew? Okay. The high state, again, we see lower cooperation rates the first time we enter the high state, and overall lower cooperation rates in the high state. Surprisingly, conditional on getting into the very high state, we actually have more cooperation. if you look here at the white versus the black dots, what are the white dots? This is the cooperation rate in period 3, conditional on being in the very high state. So I have to have done CC in low, CC in high. So what do I do? Well, we have about 50% cooperation rate. This is the white dots. So initially 60%, it goes down a lot. So it's not that stable. I have less observations here. But in subsequent periods, conditional on still being in the very high state, this actually increases. So conditional partnerships that manage to sustain cooperation, they need to go through 2 filters where some of the less cooperative people peel off. I get more cooperation in this very high state. Very low, most people cooperate. It's a dominant strategy. Okay. Here, I can't show you a 4-dimensional graph. I'm pooling the cooperation rate in the very low and low states and the very high and high states. So this point here would be the Markov perfect equilibria. If I estimate strategies by the strategy frequency estimation method, what do I find? Well, about 30% of the data is these Markov strategies. But unlike the game with the shocks to the payoffs, where I was getting the cooperative Markov outcomes, here, half of this Markov behavior is on a Markov strategy which produces outcomes which is worse than the Markov perfect equilibria. This is consistent with an asymmetric Markov perfect equilibrium profile. If you matched this with a strategy MCD-C-D, this would form a subgame perfect equilibrium. So subjects seem to be more pessimistic in this game with more states. They're cooperating less from the very first period. So I don't have enough treatments to tell you where this is coming from. One potential source is that I have to form conjectures over where I'll be much further into the game. It could be that subjects are being more pessimistic about where they think they'll be in subsequent periods, which is driving them to defect in the very first period. It could also be that I added a state below, and now they think they're meant to alternate between low and very low. I don't have enough treatments to pin this down. It suggests that adding more states makes people initially more pessimistic. Okay, so I don't get 50, 60. Oh, there's a question? Okay, we can come back to it later. Okay, so though I don't see a stark increase in selection from the very first period of the Markov perfect equilibria that I like, the symmetric one, we do see a much greater miscoordination in this game. That after the first couple of periods, the behavior looks like Markov strategies. Many of the strategies people select miscoordinate and revert to a Markov profile. So in the steady state in this game, the behavior does look much more Markov-like, MPE-like, in fact.
Where do we see the miscoordination in what you showed us before?
It's not here. If I show you sequences of behavior and I look just at rounds 3 onwards and I estimate this again, I get more action on the Markov strategy. If I look at sequences, I get more alternation between the low and high states, which is consistent with, I also get more alternation between the very low and low states, which is consistent with the asymmetric Markov. So I'm not showing it to you. You're going to have to trust me on this one.
But you'll want to
present the evidence.
More
Okay.
formally, right?
Yes. Oh, you think that would be that's the thing we should take away from this?
Well, if
Yeah.
you're presenting it as
A core result.
conclusion, you want to
Yeah.
establish it with
Okay.
more than just eyeballing things.
Yes. I should do that. It's in the appendix, actually, so we should probably move it somewhere more prominent. Okay. Okay, so 2 additional experiments that I added to my... Oh, there is a question now.
The people who are coordinating with the very high speed, it's not represented
They're a fairly small fraction.
yes, but okay, but
Or successfully, yeah.
it's maybe that they are
They are represented here, in fact. Yeah.
they're coordinating with the
This strategy cooperates until it observes a previous history where we didn't both cooperate. So these are the ones that would get there. So yeah, sorry, I got confused.
Is there a research about people like diverging? There is some kind of divergence in the last like was there some much success on background and strategies?
So this is how sophisticated subjects are, or intelligence and...
Getting more surplus from the people who reach the very high cooperation get much more surplus than
The people who get the most are in fact those who manage to deviate in the high state and manage to sustain this alternation between CD and DC in the high state. They actually do better. That's where the efficient frontier is. So it's not the smartest thing to do joint cooperation. But I don't have any background characteristics of these people. I don't have anything that can explain how their sophistication... but between the strategies selected. Do you collect any in your games? Did you collect any in your games? To and they know this? There's common knowledge of this, or? Yeah. Yeah.
But I'm trying to remember, in our survey, I remember we didn't find any paper that looks at these types of questions where it matters unless people are sold. Yes. But I can't remember exactly what they looked at.
So, yeah, they would know. Okay, so that's actually the last treatment in this paper. So there's no more of this paper, so we don't have to see this weird spider diagram again. But it motivates this distinction between games with just shocks, independent shocks, which are producing the richness in the state, and those which have richer endogenous dynamics. So I'm going to now look at some other papers through the lens of this dichotomy and try and see if we get more collusion in games with just exogenous shocks, and whether we get more pessimistic Markov-like play in games with richer, endogenously reachable states. So I'm going to look at the first one. The first paper to really look at Markov perfection in the lab, with a random termination game, was this paper by Marco Battaglini, Salvo Nunnari, and Tom Palfrey. It was originally a working paper back in 2009. Now it's a 2014 working paper. It's based on their AER paper on a dynamic free rider problem. So they're going to examine a dynamic public goods. The round payoff is going to be given by their consumption plus alpha, some weight, times the square root of the stock variable. So C is my level of probabilistic consumption, S is my stock. Payoff for the Supergame, just the discounted sum. So C is the personal consumption. They're going to get a flow income of W. They're going to choose to put the residual into the stock. So they're going to get an income each period of W, and then they're going to make a choice of private consumption, and the residual is going to be put into the public good. Pardon, I can hear. It's just a parameter weight. It's like how much. I can't hear. Sorry. Yes. Yeah. It's just a weight relative to consumption. Okay. So the public good. It's not going to degrade here. It's just going to be a durable public good. We're just going to add, for each of the n participants in the game, we're going to add their contributions to the stock. So this is, we can think about the public good as being the number of pictures in a gallery. If someone uses their surplus income to buy a picture and give it to the gallery now has additional pictures, which everyone likes to go see. Or giving parkland, giving buildings, giving other elements to the public good. So like a standard public goods problem, there's going to be a static externality. So we internalize our opportunity cost of contributing. We don't internalize the public benefit. But there's also here a dynamic externality in that my contributions today are going to affect contributions of others tomorrow because they're going to increase the stock. There's a diminishing returns to this stock. So there's a form of dynamic crowding out here. A social planner here would have all of the agents fully invest their public good until the marginal cost equals the marginal gain. So we're going to have some steady state level of the stock for a social planner given by this expression. Individuals will instead look to maximize their own payoffs. This is fairly standard. So they're going to only take a marginal gain of 1/nth the size of the planners. But they're also going to have to account for how their behavior affects future contributions of others. The first case that they look at is the case where contributions are going to be reversible. So this is like me giving a picture to the gallery and it says that it's on loan from me. I can pull this picture back at any time. So my consumption is going to be between 0 and my income W plus my share of the public stock, S over N. So they call this the reversible investment case. So agents can remove their share in any round. And in the model, they can continue to remove their share, so more than their share. Okay, so they motivate this reversible investment case through like publicly owned parks, which we give to private developers, removing laws that we previously had limiting over extraction of a stock, etc. Okay, so looking at the symmetric continuous MPE, they're going to put another restriction on this, that they're going to require that the individual's value function is concave. With all of these restrictions, they get a unique Markov perfect equilibrium. Strategies are only going to depend on the last period stock. So the current period is determined by how much we give. So I'm going to condition my response on how much there was in the public good yesterday. Here they characterize the equilibrium path. It ends up being that the final level for this stock is much lower than the planner's level, obviously. And here, this is the maximum level that the stock can get to. So they end up contributing all of their endowment until they reach some level. It's just that this level will be very small. So for the values in their experiment, n equals 3, a 3/4 continuation value, and alpha equals 4. The upper bound on this is 7.1, whereas the planner's solution would have continued all the way to 576. I think their income each period is going to be either 16 or 20. So first period they'll give a fraction of their income and they'll never give anything again. They have another case where we have irreversible investments. If I give you something, you're not allowed to take it back. So my consumption is constrained to be between 0 and my income. So here you've got no fear that your contributions will be expropriated by others. So they come up with another steady state investment level. And here at the same parameters, we find out that this is 64. So again, it's obviously less than the planner's level. Okay, so the MPE predictions here have the ordering that the irreversible investment case is less than the planner, but larger than the reversible investment case, which is larger than 0. Okay, but the best case subgame perfect equilibria are going to be different. Why? Because in the reversible case, I can use history-dependent strategies to punish you. So if we don't go along with the agreement, we can take the stock down to 0. Okay, so if I look at the best case subgame perfect equilibria, we have the opposite ordering. Okay. I'm just going to go on to the experiment. So they use Caltech students. They're going to have groups of 3 or 5 individuals. They run 10 super games, random rematching between them. Continuation, like I said, was 3/4. In the 3-person groups, their income is 20. In the 5-person groups, their income is 16 each period. And they're going to look at the irreversible or reversible environment. So there's 4 treatments: irreversible, reversible, 3, and 5. Yeah.
You showed us lots of evidence that you only expect that if this best case is sufficiently good and otherwise.
Yes.
I know they didn't attempt to look at with knowledge, but have you or anyone else? And I think it would be helpful
when we get to the results. We're comparing apples and oranges, and maybe it's a little bit unfair. No, I think this is going to be a very good criticism of this, and it's going to motivate the work that came after it, which is what I'm going to do. This is, yeah. Okay. So the dynamic freerider, the predictions under the Markov here with 3, we have 7.1. With 5, we have less at 5.54. Whereas the planner's solution is much, much higher. The irreversible case, this is invariant to the group size. We get 64. Again, this is far below the planner's solution. The planner's solution will be attainable with history-dependent strategies and delta large enough. Okay. I'm going to skip this. So here, this is, I don't have access to their data, so I can't make nicer graphs. So here, IIE is irreversible investment equilibrium, RIE, reversible investment equilibria. So the dashed red line and the dashed blue line are the Markov perfect equilibrium predictions for these games. The solid lines, the blue and the red, are the behavior of the median subject over time, or the median group over time, sorry. This green line is the optimum. So what we see is that the reversible investment case, with which could be doing much better with its history-dependent strategies, is down here near the bottom limit, whereas the irreversible investment case, it's certainly not fully efficient, but it does much better. If we measure this relatively, if we normalize this by looking at the stock minus the Markov level divided by the planner's level, minus the Markov level, we see that it's about 60% efficient in the irreversible investment case and close to Markov in the reversible investment case. So this is maybe getting at Drew's point that maybe it's a little bit unfair to look at the reversible investment case where there's this fear of expropriation, where the strategic uncertainty may be very prominent, and so people move to the less cooperative outcomes. This is your... And they don't really talk about the other possibilities too much. No, this is... we can shoot this down and move on to the next one. But I think this is they started out with a game that they were interested in, which is a stochastic game. It was far off from anything we really knew about, which is why I've tried to start from a place that we already knew with Prisoner's Dilemmas and try and work outwards. Here we jumped into stochastic games, and it's unclear how to think about some of these results. Okay.
In the irreversible game,
Yes.
do you know how much is driven by group cooperation and how much by one or two hopeless optimistic people who always contribute?
I can see the proportion of people who contribute. I'll show you that in a second. I don't have more particular data. Most of the stuff they're giving within the paper that I can use to sort of understand this is over the median subject. So I can tell you what the median is contributing. But so within a group of 3, it's certainly telling me that 2 people cooperating. So it's not one outlier. Okay. So then in 5, I'm going to skip that. Median individual's investment through time. So this is what you were asking. So in the IIE, they start out giving most of their endowment. This is with n equals 3. So they're giving most of their endowment. And then this is dropping through the course of the game. Here in the reversible investment case, they start out giving something. And then everyone gives nothing. Or the median subject gives 0 and then begins to extract at the end. I'm going to skip that. Okay. So if I look in the reversible case in round 1 of the super game, 2 to 4, 5 to 7, and 8 to 10, well, in the reversible investment case, in round 1, 100% are giving something. Everyone's giving a little bit, and then it's dropping down. But on the other side of the coin, there's a fairly large fraction of people who start taking. Once we see people start taking, maybe this is driving us towards the Markov perfect equilibrium, making it harder to coordinate on cooperative outcomes. Okay. This is the same thing for the irreversible case, where there's no possibility of people taking anything, so this shifts that weight somewhere. It doesn't shift too much of it towards 0. People continue to give in this game. They do show that many people look like conditional cooperators. So here, they're going to run a two-bit regression on what was given last period. I'm going to regress how much I gave this period on what was given last period by the other players. They're going to find that a number of subjects act as conditional cooperators in this game. So, so there is a fair amount of history-dependent strategy in the irreversible case. There's not much in the reversible. Okay. One thing they do to try and get at Markov in this paper, they take the infinitely repeated game, the stochastic game, and they move it to a one-shot problem. So they're going to ask people to make a choice of consumption, where this is their payoff. So they're going to use this V of R function as the Markov perfect equilibria value function. So they're going to try and reduce it to a one-shot. So what they do is they form in the reversible case, the case where they were getting behavior that looked like Markov. They look at groups of 3 and 5, and then they give them a starting stock of 0 to 35 in increments of 5, and then see what choice of consumption they make. Under, the particular concave Markov that they take. And then they create the one-shot game. I haven't seen their instructions for this. I looked. I don't know how... Yes, it's exactly what Cooper and Kuhn did. So they're just trying to get at, do I approach this in a one-shot Markov way? Does the behavior in the dynamic game look like the behavior in this one-shot game? So this is the graph that they're going to show you. They'll look at the behavior in the one-shot game. So for each of these different levels of the initial level of the stock, what's my choice of contribution? What's my behavior in the dynamic game? What's the Markov perfect equilibrium theory? So in the treatment where the behavior did look like Markov on the stock, the one-shot also looks like this. So they use this to say that we get Markov perfect equilibria in this game. That behavior in the static game looks like the behavior in the dynamic one. Okay, so there's a lack of precise evidence for strategy choices in this game. They conclude that the outcomes are well ranked by the comparative statics produced by Markov perfect equilibria. But there's not much examination of the strategies that people actually use in this game. Plus, it's unclear which features might be important within this game for driving that selection. There's more than 2 participants, there's a continuous choice of contribution, there's a continuous state, I can expropriate what others have given. There are lots of features, we don't know which particular one might be driving this selection. So we want to try and look at something which can maybe use features of the lab to try and get around some of these questions. Okay, so I'm going to now look at another paper by Emmanuel Vespa that looks at the dynamic common pool, which is going to try and do this. It's going to use more features of the lab to get at the strategic choices in these more complex games. So the game he's looking at, Livari and Merman, Bell Journal of Economics, basically, okay, we're going to look for a Markov strategy. If I skip the slide. Oh. So each period, I'm getting alpha of S. I didn't set this well up. So I'm going to have, there's going to be a stock variable. I should have put this on the slide. I don't know why it's here. So there's a stock variable. I can choose how much to extract from this stock. The amount that I extract from this stock is going to come to me as a payoff with the log of that extraction. So this is my contemporaneous payoff. And then what I've subtracted from the stock, that stock is then going to grow at a rate of 1 plus R. So R is the rate of growth for this stock variable. That's here. This was the original stock. If we're following a Markov perfect equilibrium, we're going to subtract with 2 players their share that they consumed. This is then going to be multiplied by 1 plus R. That's going to be the stock tomorrow. If I wanted to solve this, I would look for a one-shot deviation. So I can try and take a first order condition of this expression. This is going to give me this equation. I can guess in this log case that it's going to have a linear solution. I would solve for alpha with this first order condition. I'm going to find out that alpha is equal to 1 minus delta over 2 minus delta. So the slides are going to go through this derivation. So this is a guess and verify solution to this equation. The social planner is going to choose a different amount because here, when I take a derivative, well, I'm going to take into account the other person's extraction as well. The social planner, therefore, would choose a share 1 minus delta on 2. So Emmanuel took this game and he didn't want to have a continuous action choice. He's going to discretize the action choice to just be one of 2 choices. Extract a high amount or extract a low amount. And as a treatment, he's going to add a third action, which is take a large amount. This is going to be something we can use to punish. So he's going to set the take a small amount to be equal to the planner's solution. He's going to set the take a medium amount to be the Markov perfect extraction. And he's going to take the large amount to be, let's take half the stock. If we both take half the stock tomorrow is going to be 0. 0 can't grow that well. Okay. So if you choose the extraction level an eighth, you're going to get an eighth of the value of the state. Your payoff is going to be the log of that. Unfortunately, in the lab, we can't give people large negative payoffs, especially unboundedly large negative payoffs. So he's going to have to try and limit how low the stock can go. So in order to do that, he's going to first round these stocks to be integers. So he doesn't want to present them with irrational numbers. So he's going to give them an integer stock. So this is going to be how the transition works. And additionally, if the stock ever gets below 8, he's going to move the stock variable to 0, and he's going to modify the payoffs so I don't get the log of 0 as my payoff. So if the stock reaches 0, my payoff is 0. Why does he do this? The lowest I can extract is 1/8. 1/8 times 1, log of 1 is 0. Yeah? Okay. So evolution of the state. So for efficiency, we should both select C, and then the state is going to grow at a rate 1 plus R, 1 minus 2/8. So this is going to be 3/4. So each round it's going to grow 1 plus R times 3/4. For the MPE, we get a similar equation. If I plug in the numbers, this is going to be 3/4 1 plus R times the previous round state, 3/5 times 1R plus the previous round state. There's also going to be a depletion MPE. Because he put this lower bound at 0, and he stopped people from getting unboundedly negative payoffs, there's also going to be some other Markov perfect equilibria which emerge, which are going to be threshold strategies. If the state ever enters some region, I play H. If it's above that region, I play M, or in some of his treatments, he's going to actually cooperate. Okay, so that's the setup and motivation for his game. So this is going to be a continuous state. So this is the richness of this game. His treatments. He's going to start out with just an interest rate of 0.92. The C action is an 1/8. The M action is a 1/5. The Markov perfect equilibrium, the delta he picks, is going to be giving us 1/5 here. He adds a third strategy. So he adds the ability to punish with this high extraction amount. He has another treatment where he decreases the interest rate with these same variation over the amount of extraction. He has a treatment here where because he's discretized this, he can push the Markov perfect equilibria down to have more extraction, so there's going to be more difference between efficiency and the Markov level. So he increases the M extraction level from 20% to 25.5%. And then finally, he has a treatment where he matches the Markov perfect equilibria, characterized by Levari-Merman, to be the same as the efficient solution. So he just has two actions, extract an 1/8 or extract a 1/2. So this is what the stock looks like in his baseline. So if we're cooperating, we're growing this state so that we're going to get... This is just the equilibrium, yeah. Otherwise it would be far too smooth. So under the efficient solution, we're going to grow this state by only extracting a small amount, whereas in the Markov perfect equilibrium, we're going to be extracting more so it grows less quickly. So in terms of payoffs, what does this mean? It means that when I'm cooperating, I'm playing the efficient solution, I get lower payoffs to begin with, and then they become larger. Yeah? So I have to give up some initial periods to grow the stock, so I can then start to get larger payoffs later. This is with the low growth rate. These things don't take off as much, so this is 0.57 instead of 0.92. This is difference between efficiency is larger. He changes the extraction in the Markov so that now there's a larger difference between efficiency and the Markov solution. And then in his final treatment, the Markov is coincident with the efficient solution. Okay. There's these additional Markov perfect equilibrium in thresholds. I'm not going to focus on those too much. But this is his main construction. So if we're looking for Markov, we should be seeing more M actions. In this T3 treatment, we should be looking for the C action. Just take an 1/8. Okay. In terms of efficiency loss, these have a constant efficiency loss between the cooperative and Markov solutions. It's larger here in T1, though the level is smaller. And here in T2 is where it's largest. This is one where we're creating the largest distinction between efficiency and Markov. Okay, this is what his screen looks like. So you're choosing whether you're going to take in the first round 20% or 12.5%. This is his T0 treatment. This is a complicated game. You have to think about where you're going to be going. So he introduces a device for subjects to calculate hypothetical futures. So they can right-click. I believe it's right-click. You've used this interface, yeah? I think you right-click on each of these things, it creates a hypothetical, and you can go into the next period and see what the stock would be, see what the temptations would be. So that's one thing he does to make this environment easier for subjects to deal with. Given the very rich set of states, I'm motivated from looking at Marco, Tom, and Salvo's paper that it was hard to really get much information on what strategies were being selected. One thing that would help would be if we can use the tools of the lab to ask people to make contingent choices. What are you going to do tomorrow if the person selects a high extraction? What are you going to do tomorrow if the person extracts a low level? So he introduces a one period ahead strategy method. He's not going to get the entire strategy, which has to tell you what to do at each possible history, but along the path he's going to get all of the nearby histories what you would do. Okay, so this is what it looks like. After round one, where you make your natural decision, you're going to make a decision on what to do in round two in response to each possible other choice by the other participant. So here, if the other decides to take the cooperative amount, what are you going to choose? These are going to be the stocks. These are going to be your choices. What are you going to do if they took the high amount, if they took the medium amount? Yeah? So we're all seeing what he's doing. Okay. He does this with an infinite time horizon, with random termination, or a mix of random termination. The first couple of periods are actually the first 6 rounds. He discounts the amount of money that they're earning. So I'm going to, in round 2, the payoffs are going to be multiplied by 3/4. In round 3, it's going to be 9/16. Until round 7. In round 7, he switches from payoff discounting to random termination. So we're guaranteed to have these 6 periods. After that, it's random termination. So the average length of these interactions is 10 rounds. Okay, so did I say anything else? All of his estimations, or the estimations I'll mostly show you, are going to be off of the last 4 super games, where he's going to use this additional information on contingent choice to help him pin down what the strategy is. He has 3 sessions per treatment. They earned about $30. They were in the lab for 2 hours. It's a fairly long experiment. Okay. This is what the stock looks like. So here, again, I don't have access to his data, so I have to use the graphs he has. So this is why they look like they were copied. So here we have the efficient solution. This dotted line is the MPE that we calculated. These red points are the average stock, the observed mean of the stock in each of these periods. So it certainly looks like it's closer to the Markov here than to the efficient solution. If I add 3 actions so that I can choose to deplete the stock by taking a half of it, well, the mean is below the Markov perfect equilibrium level. In the treatment where the growth rate is lower, it's more in the middle. We saw that the efficiency difference between the planner's solution and the Markov was larger here. So there's a larger separation. With 3 strategies, this is lower. There are more people playing the take half action. T2, this is where I made the Markov extraction level larger. So there was a greater difference between the efficient solution and the Markov. Here, we do see behavior increasing. There's more cooperation. There's more extracting 1/8 of the stock instead of 1/5. And in T3, this is the one where the Markov and the efficient solution are coincident. We see that they're cooperating. They're not taking a half of the stock until these last periods. I don't know what that is. It seems that some people towards the end of the game are playing the depletion level. Okay, he estimates, let me show you the last 3 super games. He estimates the percentage use of the Markov strategy towards the end of the game. Or this is just showing you the levels, in fact. So here, in T0, T03, T1, T13, 80 to 88% of the subjects, they're using the Markov extraction level of M. There's a much lower incidence of H, of taking half the stock. There's some incidence of the cooperative level, particularly in T2, where there's more incentive to move away from Markov. Estimating the strategies, given these levels, unsurprisingly, he finds a large incidence of the Markov perfect equilibrium strategy, which is all M in T0 and T03. In T1 and T13, there was a larger difference in terms of efficiency. He still finds that the modal strategy is the Markov one, but it's reduced somewhat. He actually finds slightly more use of unforgiving strategies. So these are once they go to the punishment, they don't return to the cooperative level. In T2, where there's an even larger difference between the efficient and Markov levels, here he finds 40% of the Markov and much more on these unforgiving history-dependent strategies. So here, the power of the one period ahead method is allowing him to estimate these strategies with greater confidence. Okay. And T3, so he does find like 50% cooperative strategies here and a large incidence of Markov. There's a depletion Markov here. Choosing to take H in the very first period, this is one of these threshold depletion Markov strategies in this particular treatment. Okay. Says findings. In his game, the modal strategy in every treatment is the Levari-Merman Markov perfect equilibrium. As the incentives to cooperate increase, the frequency of this Markov decreases. The frequency of unforgiving history-dependent strategies increases. Across sessions, he finds that subjects increase their use from the beginning of the session towards the end. They start out more history-dependent. They move towards the Markov strategy. Strategies which are forgiving, those which have a punishment for a while and come back to the cooperative path, become less common too. Okay. So the MPE is very commonly selected here. So in this rich environment, he finds that Markov is a good predictor of the outcomes, or Markov perfect equilibrium is a good predictor of the outcomes. So taken together with the Battaglini results, his reversible, the Battaglini et al. Results, with the reversible, it does look like richer, endogenously reachable states do push the game towards Markov perfect equilibrium. Okay. This comes up against the fact that in our treatment that I showed you where we turned off the static externalities, we also saw a large push towards the Markov perfect equilibria. So in his game, there's no static externality. Like my consumption today doesn't affect your payoff. It only affects our future through the evolution of the stock. So it's not clear which one might be driving this. Ours has an asymmetric. Ours has the Markov perfect equilibrium being the most efficient symmetric solution, which may be why we're getting the behavior we're getting. There's a low difference. There's a small difference between Markov in our game and an efficient solution. So I'm just trying to bring these two results together. Okay, so those are the papers that look at these rich endogenous dynamics. I'm now going to look at games which have much simpler endogenous evolution of the state, but they're having a richer set of shocks. I'm going to have to go a little bit quicker here. So Vespa Souls, this is a game which is going to look at structural estimation through an experiment. It's going to take a very commonly studied entry-exit model of competition, and it's going to put it into the lab. This model of competition is going to look a lot like a prisoner's dilemma with an additional feature. Okay, so their main motivation is to examine the effects from assuming symmetric Markov perfect equilibria in these structural econometric exercises. Okay, so they're going to have two firms, 1 and 2, two firms, we'll call them 1 and 2. They're going to have time periods, 1, 2, unbounded, delta equal to 4/5 in their game. The states of this game are going to be for each of the two firms, they can be in the market or out of the market. So there are going to be 4 states, both in, both out, and then the 2, 1 in, 1 out. On top of these 4 endogenous states, we're going to have shocks each round, X, which are going to be what's the scrap value of my business if I'm in the market, what's the entry cost if I'm out of the market. At time t, both firms are going to start in the market. So the state S, the endogenous part of this state, is going to evolve according to the firm's entry and exit decisions. So the sequencing of the game is they're going to make decisions over quantities. They're going to choose a high or a low quantity. After the resolution of these quantity decisions, they're going to make a decision about whether they're going to enter or exit this industry given their draw of the scrap value. If they're out of the industry, they're going to be deciding whether they want to come back in. Okay, so they're going to set this up as a prisoner's dilemma. They're going to have effectively a high and a low quantity. We can think about... Yes.
That's correct. So if I go in and you're out, there's no market.
Yes, I just choose the monopoly quantity. Or.
You do produce. It's not.
Oh, yes.
But you're saying it's hard coded. You automatically make an output.
Yes, you don't have to make a choice there. Okay, so if they're both in the market, the quantity choices are going to look like a prisoner's dilemma. So we can choose the collusive quantity, or we can both choose the high quantity, and we can end up with a lower payoff. So we would like to collude if we can. The Markov perfect equilibria is going to assume that we're, through state dependence only, no history dependence, that we're going to play the standard oligopoly quantity. So we're going to put in D here. So he sets this up with some parameters. The point of this is he wants to estimate things. So we want to have something that we can estimate. So he's going to have A, that's going to be the market size. He's going to have a low, a medium, and a high. We have rho. This is the effect of competition in this market. This is if the other person is producing, what's the effect on me? And he also has another parameter tau, which is going to be a fixed cost of entry. So here it is. So in this second stage, firms in the market, they're getting this IID uniform shock. They can choose if they exit, they're going to get a payoff of 100 times X. If they're out of the market, this shock is telling them they have to pay 100 times tau. Tau is going to be 0.15 here, so they're going to have to pay 15 for sure, plus some other amount depending on the shock. Okay. Okay. So by the assumption for Markov, this is if they're both in the industry, their payoff is going to be this amount. It's going to be the DD payoff. If one of them is going to be in, they're going to get the DC payoff. And if neither of them are in, or if they're not in the market, sorry, if my state is out, I'm going to get a payoff of 60, regardless of if the other person is in or not. Okay, so given these values, we want to find out the optimal policy for entering and exiting this industry. We can solve this Bellman equation. We're going to find some minimum shock for exiting, and above this level, we'll always choose to exit, and some maximum shock for entering. So, and below this level, we'll always choose to enter. We can think about this optimal policy as just being a probability of transiting between these states. So, given that I'm in, what's the probability that I'm going to be out tomorrow? Given in out, what is the probability, etc. So here, given these levels of the state, we're going to have, by computing the Markov perfect equilibrium, we're going to have some transition probability between these states. If I'm an econometrician, I can observe the frequency with which firms are entering and exiting the industry. This is why this model is being set up this way. I have access to a small amount of data. I might like to use that data to try and work out what might be true in the world under the structure of the Markov perfect equilibrium. So, given some empirical frequencies, I might try and invert the value function and then try and predict possible choices. And then I'm going to try and minimize an objective function to estimate A, tau, and rho in this case. Okay, so the paper shows through a Monte Carlo exercise this is consistent. I mean, otherwise they'd be upsetting the I/O world, I guess. So they're not going to revolutionize that. What they do show is that if we instead chose collusive outcomes in this game, we would get very different probabilities. I'm going to be running out of time in a second. So what they're going to show is that if we followed a collusive outcome, these probabilities would be quite different. If I were to make the assumption that these probabilities came from the Markov perfect equilibria, my conclusions about the parameters A, rho, and tau might be off. In particular, they show that this B parameter is what I'm calling rho. They're going to show that as collusion increases, I'm going to underestimate the amount of competition in this, the competitive externality in this market. So this line here is the rho. If there's no collusion, its value is close to 0.6. If there's full collusion, its value is much closer to 0.2. Yeah? So this is going to be what they're going to try and set out to do. They fix rho at 0.6 and tau equals 0.15 for this market. As I said, they have 3 sizes of market. What is this going to look like? In the small market, there's high incentives to collude. In the large market, these incentives are such that it's not a subgame perfect equilibrium to collude. Yeah? Okay. This is the basic setup. They're going to run this over 2 setups. They're going to have the standard one where they can make quantity choices. I can choose high or a low quantity, cooperate or defect. And they're going to have an environment with no quantity choice, where I have to pick the Markov perfect equilibrium outcome. So here they're going to have the theoretical predictions on these transition probabilities in the Markov perfect equilibrium and the collusive equilibrium. Is it an SPE? What are the gains from collusion? I'm going to be running out of time in a second, so I'm just going to move on a little bit. Okay, they have 14 subjects per session, 3 sessions per treatment. They're going to use delta equals 0.8. They have 16 supergames. In the first supergame, they're going to give them the entry and exit cost each round and ask them if they want to enter or exit. In the remaining 15, they're going to use a strategy method, and they're going to ask them, tell me the maximum shock for which you would like to enter the game. Tell me the minimum one which you would like to leave the game. Okay, this is what the environment looks like. They make choices. This is what the screen looks like after they've made their choices. They come to this screen. It's telling them what their, in the first period, what their shock is. Would you like to exit or would you like to stay in? Okay, results. Collusive quantity choices. So in the large market where there's lower incentives to collude, they get about 20% collusion. They're defining collusion here as in the very first round of the game, do I choose the cooperative quantity level? Here in the medium market, it's larger, and it's about the same in the small market. This is across time. Okay, so the strategies they find people using. Well, in the large market, they're mostly playing always defect. In the smaller market, it's slightly lower on always defect and larger on strategies like tit for tat and grim. Okay, the quantity stage decision. This is where the game is different. This is where it has some interesting dynamics. They do find, sorry, I'm confusing myself. This is the entry-exit rates here. So here, what am I going to show you? This is what's the probability of being in the market, conditional on my being in and the other person being out. This is the best case for me. I'm getting the monopoly quantity. What's the probability if we're both in the market? If we're both out of the market, and if I'm out of the market and the other person is in. Yeah? So in theory, we should have a decreasing probability of being in the market across these four. In all of these treatments, they find that comparative static. In some it's significant, in some it's not. What they find is that there's a greater amount of inertia. That if I'm out of the market, I go into the market less often than I should. I stay where I was. The same thing holds true for being in the market. I exit less than I should. Okay. So I'm really running out of time. So let me just try and summarize what they do briefly. They estimate the parameters using the Markov perfect equilibria structure of Bajari, Benkard, and Levin. They pull out these estimated parameters. They find that the comparative statics aren't too bad over the A parameter, but there are large differences over tau, obviously coming because of this inertia in the game, and rho, because there's more collusion in the small market. What they then do is they take the estimates and they try and run counterfactual exercises. They say, what happens if I moved from the large market to the small market? What would happen? And they're going to scale the estimated parameters the same way as their induced parameters. And they're then going to see in the counterfactual under Markov, does it look like behavior in the actual game? Okay. What they're going to conclude is that collusion does not have a large effect on the Markov this machinery for estimating games. That even though they have collusion, it doesn't affect this econometric exercise too much. Okay. Let me go through these too many slides. Okay. So, overall conclusion. Let me just briefly sum up for an additional minute. I promise to stop after that. Subjects in stochastic games are capable of using history-dependent strategies. However, selection of symmetric Markov perfect equilibria is also common in these games. It depends on structure of the strategic externalities. Strategic tensions that attempt to cooperate, that make attempts to cooperate more risky, do help to predict the selection of Markov perfect equilibria. A very simple basin of attraction extension from Guillaume's work in Encyclopedia Games does have predictive power. Right now, we don't have a lot of work. This might be a good rule of thumb that integrates many features of the game and makes a prediction. In games with greater state complexity, where this complexity is endogenous, we do find a shift towards the Markov perfect equilibria. In games where it's just shocks, we do tend to see more collusion so long as the scale of those shocks isn't too large to destabilize it. So we may be able to use these basin of attraction indices to try and see what kind of shocks will reduce cooperation. Okay, and the final thing that we got from this Vespa cells argument is that maybe the discipline that Markov perfect equilibria puts on environments and its simplicity is more useful than the loss we get when we have to take much more complicated assumptions to work out what's happening in these I/O problems. So that there's a reason we're picking these simple solutions. There's a trade-off between simplicity and tractability. Okay, so I'm going to stop there because I'm out of time. Okay, thanks.